All right, let's just dive right into this explainer. We're looking at the hidden rules governing everything around us, specifically for 7th grade physical science. And while we'll touch on the big, broad rules of the universe today, our main goal, the real focus here, is zeroing in on how energy and chemical reactions interact. Specifically, we're talking about the hard evidence for endothermic and exothermic reactions.
So I want you to ask yourself this really big mystery. How do things we can't even see cause the massive, undeniable changes we witness every single day? Think about it. We see fireworks explode with incredible heat, or we grab a chemical ice pack and feel it suddenly turn freezing cold. But the real action? That's happening at a level entirely invisible to the naked eye. Our goal here is to connect those microscopic actions to the macroscopic energy changes we actually feel in the physical world.
To figure that out, here's our agenda. We're covering the rules of the universe, forces and interactions, energy and system changes, investigating chemical reactions, waves and information transfer, and finally, designing the future.
Okay, Section 1, the rules of the universe. Let's take a quick look at your course roadmap.
Here is our 32-week journey. And while we cover a lot of ground, forces, waves, energy throughout the year, our absolute main focus today is going to be right there in Unit 3, where energy and chemical reactions perfectly overlap.
Moving right along to Section 2, forces and interactions. Basically, why do things move or crash?
That leads to our essential question for Unit 1. How can forces explain changes in motion? You'll be answering this by looking at actual, real-world systems. You aren't just memorizing formulas from a textbook here, you're planning investigations to see exactly why an object's motion changes based on the literal forces pushing and pulling on it.
You'll interpret motion data to figure out why a particular object stays put versus why it suddenly accelerates. Look, when forces are perfectly balanced, things are peaceful, right? They sit completely still, or they just keep cruising at the exact same speed. But introduce an unbalanced force, that's when things get exciting, and objects suddenly speed up, slow down, or completely change direction.
The absolute crucial takeaway here is Newton's third law. For every action, there's an equal and opposite reaction. You'll actually use this to understand impact forces during collisions, much like real safety engineers do. But let's keep moving, because once we understand motion, we really need to look at what's driving it all.
Which brings us to Section 3, energy and system changes. We have to answer the question, where exactly does the energy go?
You'll trace how energy transfers from one system to another, basically proving that energy doesn't just vanish into thin air, it just changes form. For example, if you double the mass of a moving object, you double its kinetic energy. But if you double its speed, its kinetic energy literally quadruples. And beyond just large objects moving around, it's absolutely vital to recognize thermal energy. The invisible movement of particles at the microscopic level dictates the literal heat we feel, which sets the stage perfectly for our chemical reactions.
You'll plan investigations to see this thermal energy transfer in action. Take melting ice, for example. It absorbs heat from its surroundings. That is a classic endothermic process. By tracking the final water temperatures in different experimental setups, we gather hard, undeniable evidence of exactly where that invisible energy went.
Now for Section 4, investigating chemical reactions. How exactly do invisible particles create visible changes?
Here you'll develop models to prove that matter never magically disappears during a reaction. Whether a reaction releases energy out into the environment as heat, which we call an exothermic reaction, or absorbs it, making its surroundings colder, an endothermic reaction, the atoms are really just regrouping. The total mass is always perfectly conserved. By analyzing data before and after doing something like burning steel wool, you get to act as a chemical detective. The heat released during the burning, that's your hard evidence of an exothermic reaction. Meanwhile, a sudden change in density tells us a brand new substance is formed. We track these visible, macroscopic properties to prove the invisible particle changes happening behind the scenes.
All right, Section 5, waves and information transfer. Ever wonder how your Wi-Fi actually works?
You're going to build models to understand the massive difference between the sound waves hitting your ears right now and the light waves traveling all the way from the sun. Mechanical waves need a physical material, a medium to bump into, while electromagnetic waves, they can travel through the absolute nothingness of empty space.
And you'll discover how we use these exact wave properties to send digital information through things like fiber optics and Wi-Fi. Instead of sending a continuous analog wave, we use incredibly quick, reliable wave pulses to send ones and zeros.
It's basically the scientific foundation of all our modern communications technology.
Finally, Section 6, Designing the Future. This is all about thinking like an engineer.
Let's see how all this builds into an actual, practical process. Your application task will be to use these exact concepts we've talked about to design a real device. Think along the lines of a chemical cold pack that utilizes a strong endothermic reaction, or maybe an insulated cup designed to maximize thermal energy transfer. You'll define your specific constraints, construct a solution, test it for energy changes, and then optimize it based on your results.
As the next-generation science standards point out, engineering advances have led to important discoveries in virtually every field of science. Science helps us understand the natural world, right? But engineering uses that science to solve actual societal needs. They are completely intertwined.
So, as we wrap up this explainer, I want to leave you with this thought. Now that you know the hidden rules of the universe, especially how energy transfers back and forth in endothermic and exothermic chemical reactions, what are you going to build? The invisible particles are just waiting for your instructions. Thanks for joining me, and stay curious.